So hello everyone. My name is Tom van Mele. I am the co-director of the Block Research Group, and I am also one of I'm the lead developer of the COMPAS framework, and I am part of the COMPAS dev team. And I will indeed, can you see? No. And I will indeed give you an introduction to the core part of the COMPAS framework. And I think then Gonzalo tomorrow will give you an overview of one of the core extensions of that framework. First thing is that indeed COMPAS is a computational framework for research.
Tom, sorry to interrupt you. Are you sharing full screen? Because we're only seeing this, the mini slide view.
Okay, wait.
Small live tech issues as always.
I'm just gonna share the
full screen.
A full screen, right?
Yeah, it's not gonna be an issue.
It's not entirely clear to me how. Okay, so
tech people having tech problems.
yes. So entire screen, allow, and then I'll switch here. Is that better?
Let's see. There you go. Now it's working. Beautiful.
Yeah. Okay. No, sorry. Thanks for that. So COMPAS is a computational framework for research and collaboration in architecture, engineering, fabrication, and construction. So the entire framework is very deliberately written entirely in Python to make it as accessible as possible, and especially also to make it available on all different platforms and in many different softwares. But also, of course, because Python has such an amazing scientific stack, and so for a research framework, that is, of course, a fantastic tool set to have. And then in addition to that, Python is also very good at, or very useful, or very easy for the integration of all sorts of additional libraries. And so we've made those choices very specifically, just to make sure that it's as easy as possible for everyone to actually get started with COMPAS, to get it on their computer, to use it, to exchange information, to learn from each other's code, to share their code, so to not repeat themselves over and over again, and also not others, and to be able to collaborate across disciplines, across groups. And even transfer know-how from the academic world to practice and vice versa. And a big part of that is, of course, to make sure that COMPAS, regardless or in spite of or despite this a big constellation of packages that it relies on and tools that it relies on, to make it easy installable for everyone on different platforms, so on Windows, on Mac, and on Linux. And that's something where we, of course, rely very much on some of the other tools in the open source community, such as Anaconda and Conda. Anaconda provides this gigantic scientific stack, whereas Conda is an easy-to-use package manager that then allows you to install all of these dependencies and so on with a few simple commands on any computer and on any system. I promise these are, I'm not going to show many more terminal commands than this, but I just want to point out that with this very simple command, COMPAS is installed on your computer and ready to be used. So for example, here with a simple code editor and the COMPAS viewer, with one additional command, COMPAS can then be installed for Rhino, with whichever version that you prefer. There is a little editor on the bottom right there, but that it apparently doesn't want to load. Anyway, so this just to say that once you've issued that additional command, you can start using COMPAS in Rhino. Yeah, here there was a little grasshopper box on the side, so you'll have to take my word for it. So once it's installed for Rhino, it's automatically also available in Grasshopper. And then with the following additional command, it's then also available in Blender. And then Blender is then, of course, yeah, by the way, this command is the same for Rhino, is the same for Windows and for Mac, obviously not for Linux, where at the moment, at least, Rhino is not available. But for Blender, whether this is then on a Mac or a Windows machine or on a Linux machine, COMPAS will be equally accessible and available on any computer. So with that as a foundation, so Python as an ecosystem, and then using all of the tools around Python in the open source community, we've built an ecosystem for researchers, developers, professionals, architects, engineers, everybody who is interested in doing some AEC research and collaboration, that allows people to focus really on their work and not have to worry about connecting various softwares, pulling in all sorts of state-of-the-art libraries, and how to accomplish, and not have to worry too much about accomplishing all sorts of tasks related to AEC development. The framework has, or this ecosystem has, two components. So the main component you see at the top is the core part, or the main part of or is the main library of the COMPAS framework, which, as you can see in the middle, has itself a core library that defines all the real functionality, let's say, and then a bunch of packages for CAD software integration, and then what we call the core extensions, which then tie in all of these fancy libraries like SIGA, libIGL, Triangle, Gmesh, OpenCascade, and so on. And then with that as a toolbox, let's say, many people, us included, have been building all sorts of COMPAS extensions on top of this that we have started to group into AEC toolboxes. This collection of extensions and toolboxes has been steadily growing over time since our first release, or public release, I think now just over a year ago. There are many toolboxes available. There is, of course, the digital fabrication toolbox, since we're so closely related, and also very much supported by the NCCR DFAP at ETH Zurich. Which consists of COMPAS Fab, which is a package for planning and execution of robotic fabrication processes, COMPAS RSC for HB robot control, and then COMPAS Slicer for mesh slicing and for additive manufacturing processes. COMPAS Fab is, by the way, the package that Gonzalo will be talking about tomorrow. There is a structural analysis toolbox that links COMPAS to all sorts of finite element analysis software. There is a version 1 and a version 2, with version 2 very much a work in progress, but which will bring all sorts of additional backends to this finite element analysis toolbox for COMPAS. There is a form finding toolbox, there is a discrete element modeling toolbox, and many more. Part of sharing and collaborating is, of course, also to make it easy for other people to use your tools and to use the things that you develop. And obviously, coding is not necessarily for everyone. So acknowledging that, we've also made many parts of the COMPAS framework available through UI-based tools. And so I think the most important one, or the best known one, I guess it's also the only one in official release at the moment, is Rhinovault 2, which is a funicular, is a COMPAS-based tool for funicular form finding, specifically at the moment still for Rhino. And what this does is basically it encapsulates a lot of the functionality of the COMPAS framework to allow users through a simple UI and a bunch of toolbars and buttons to push and click on to develop sophisticated funicular structures, starting from basic Rhino geometry and then some simple manipulations. So here you see diagrams in horizontal equilibrium, vertical equilibrium, a pipe diagram, and so on and so on. And so how does this work? It at its core, tools like Rhinoval 2 are based on the core COMPAS framework. They add to that a bunch of packages from this pool of extensions. So for example, in this case, COMPAS pattern for making these form diagram patterns, COMPAS triangle for constraint triangulation, COMPAS skeleton for mesh modeling, and so on and so on. And then, of course, COMPAS TNA for all of the horizontal and vertical equilibrium solving. They add around this then a layer that deals with the UI, and that is independent of the environment that it's being used in. And with that, it then makes a version of that UI available for either Rhino or Blender, or hopefully soon also in the browser. There are many more packages like this under development. There is an interactive 2D graphic statics tool, a polyhedral 3D graphic statics tool. COMPAS Form Finder will soon be released for its density and dynamic relaxation-based form finding, and always based on the same principle that it's a collection of COMPAS packages with a UI that creates a front end for them. And then by compiling that UI for different softwares, we can make that tool then available in multiple CAD systems, or in the COMPAS viewer, or potentially at some point even in the browser. And the idea also there, even people who are not necessarily coders, or who want to start with a simple UI-based tool and then transition into coding, or combine the two, that you have a very unified experience across all of these platforms and softwares. Then these UI-based tools combined with the core extensions and also the core framework have been used for multiple projects over the years, not only by the PRG, but also by various other groups, and in general in the NCCR. I'm sure you will recognize a few of these projects. Not all of them have been developed entirely with COMPAS. Some have been developed only in part, but there are really quite a few where really every single aspect of a project was developed from A to Z, with COMPAS tools, COMPAS workflows, COMPAS extensions, and so on. And the most notable project, of course, is Hilo, which was opened not so long ago, and where really every aspect of the innovations by the Block Research Group were really from form finding to fabrication to construction planning and so on, were executed with COMPAS, and especially using the flexible COMPAS data structures in the background to transfer data between various softwares, between various people within the team, between various algorithms, between various processes, and so on, really without any loss of information, even though that many of these algorithms and tools were still under development while the project was actually already happening. And this was not only the case for the researchers and the people from our group collaborating, but COMPAS also served as a hub between all of the people that we collaborated with from industry. So in terms of making data available to them in whichever format or for whichever software that was required. So that's a little bit an overview of the things that we have been developing and going from a core framework that provides all the nuts and bolts to then extensions that build upon those on that core framework to make toolboxes that are specifically geared towards AEC processes and development tasks. To then UI-based tools that make it easier for people to use all of that infrastructure and to deliver various aspects of AEC projects. And what I want to show now and focus the presentation on is basically which components of the main library or which aspects of the main library that actually provide the important aspects of that infrastructure, and that we will be further developing in the future to strengthen that infrastructure even further. So just as a reminder, in the entire ecosystem, the main library is the top that you see at the is a part that you see at the top. If we look at this slightly zoomed in, so there is the COMPAS core package, which defines what I always call all real functionality. So all the data structures, geometry processing library, numerical solvers, robotic fundamentals, topology algorithms, the remote procedure call infrastructure, and so on and so on. And then there are the CAD packages, so that provide a specific integration into Blender, GH-Python, and Rhino. Maybe a small side note there. So COMPAS is actually, you can use COMPAS in any environment that supports Python scripting. So it's not because a software is not listed here that you cannot use COMPAS there. It's just that at the moment we provide very specific integration for the ones that are listed here. So Blender and Rhino, and then Rhino and Grasshopper, of course. And then in addition to this core library, so the core functionality and the CAD integration, there are what we call the COMPAS core extensions, which provide then these wrappers for state-of-the-art external libraries like Seagal, Gmesh, libRGL, OCC, or OpenCascade, Triangle, and so on. There are two things that I want to emphasize that I think actually form the backbone for this exchange of data and exchange of information between various processes and between various softwares. And the first one is actually COMPAS Data. So there is the COMPAS Data is a package in the core framework, and there are three types of data that are based on this base data framework. So first of all, the geometrical data or geometry objects, then the data structures, and also robots. I will not talk about the robots today for the reasons that I mentioned earlier, since Gonzalo will. So this is all very much related to a COMPAS Fab, and this will be discussed at length in the talk tomorrow. What I will start with is COMPAS Geometry. COMPAS Geometry provides three, like any geometry toolbox, I guess, provides three types of objects. So the primitives, shapes, and transformations. Primitives are objects like a circle, an ellipse, a frame, a line, a plane, a point, and so on. Whereas shapes are three-dimensional versions of, or volumetric objects, like a box, a capsule, a cone, a cylinder, and so on. And then the transformation objects provide 4x4 transformation matrices. So things like translation, scale, rotation, reflection, shear, and so on. And so these objects are extremely easy to use, right? So even for those who are not familiar with Python program, this should be extremely readable. So you create a COMPAS point, which you can then of which you can then access the attributes like the X, Y, Z coordinates through normal object attribute access, which is a typical Python thing. But you can also index a point object or any other object for these attributes, such that the COMPAS objects can be used interchangeably with their pure Python equivalents. All of these objects, for example, here, vector, provide a very easy to use interface, right? Always returning new COMPAS objects and allowing you to write code in a very human readable kind of way. And this is the same for the very simple primitives but also the solids and even all of the transformation objects. where you construct, for example, a circle out of a plane and a radius, and then this plane is, of course, constructed out of a point and a normal, and then these objects are always completely accessible again from then the attributes of the parent object. With these three objects, there are, or three types of objects, there are many different algorithms in the framework. I'm not going to go through all of them. Or I'm not going to go through them. That's what I guess the documentation is for. There are a lot of algorithms for 2D and 3D predicates, transformations, linear algebra, analytical algorithms, stuff related to polygons and polyhedrons, point sets, distance, intersections, and so on and so on. I'm just going to show you one particular thing, simply to get you a little bit familiar or accustomed to the API that you can expect from COMPAS. So here, for example, it's like the point in box problem. We have a point cloud, there is somewhere a box in 3D space, and we want to know which points actually lie in that box. Right, so here is more or less the entire script. First, we have a few imports from math import radians. Is something that you get directly from Python, and then there are a few imports from COMPAS geometry. So the point cloud, because we're going to make a point cloud, then the box to do the in-box check, and then a frame, a rotation, and translation, because we're going to move the box from the origin to the middle of the point cloud. This compass view2.app thing is actually just to do some quick visualization. So here you have the box, which starts at the world origin, is a 3x3x3 box, and then the point cloud, which is constructed from its x, y, and z bounds. So it's a random point cloud of 500 points between x0 and x16, y0, y9, and z0 and z5. And then we're going to take our box that was at the origin. We're going to construct two transformation matrices, so a rotation that rotates the box over 45 degrees. Otherwise, it's a simple, or the check if the point is in the box problem is a simple x min x max problem. So we're going to rotate the box, and we're going to then translate the box from the world origin to the cloud centroid. And then so here you see those two transformation applied. Of course, first rotation, and then afterwards the translation. And then we can check for every point in the cloud if the box contains the point. So again, you see that the API is extremely readable. And then I wrote there do something, and in this case, do something in case the box is actually in the point. And so what we did here was make this viewer app, add the box to it. And then for every point in the cloud, assign it a default color, which is blue, and a default size. And then if the point is in the box, or the box contains the point, we switch the color to red, make the size a bit bigger, add the point with the color and the size, and then show this with the viewer. So this is then what you would see. So it's obviously a very simple algorithm. It's just to show you what the typical API of COMPAS looks like. And you've noticed that I haven't been using any CAD tools yet. We use the COMPAS viewer because for quick visualizations and just testing out a few things, it's often easier to just work from your editor and then launch that viewer and then visualize whatever the result of your algorithm is. And then this, the advantage of the viewer is also, compared to anything else, is that it knows exactly what to do with every single object that is available in COMPAS. So whether these are meshes or networks or point clouds or discrete element models or NURB surfaces, you just do viewer add something and it will show up. Okay, so that's all great. But yeah, we need a lot more for a geometry toolbox to be somewhat usable. And so for more sophisticated, or for any of the things that are not directly or not manageable with Python itself, we rely very much on these core extensions like CGAL, Geometry, PyGL, OCC. And these are made directly available in Compass Geometry through the plugin framework. So how does that work? Well, or maybe first a few quick examples. So once these plugins are installed, you can do volumetric modeling through constructive solid geometry, make constrained meshes or high quality meshes for FE analysis, slice volumetric objects for printing, work with NURBS curves and NURBS surfaces, which is a recent addition to the framework. And of course, also apply all sorts of Booleans to all of the base shapes and objects that are available in the geometry kernel. And this Booleans example is actually a good way to show how this plugin mechanism actually works. So without any of these backends or plugins installed, there are actually no Boolean operations in COMPAS, but it does define already a pluggable object in the geometry library, so which looks a little bit like this, right? So from COMPAS plugins, it gets the pluggable decorator, and it decorates this function Boolean union mesh mesh in the category Booleans as pluggable. Such that all of the extensions know that, or that anybody developing for extensions know that this is something that they can actually provide a plugin for. And as you can see here, in some cases, these pluggable objects will already contain a Python-based fallback, but in this case, that's not the case. So it's a not implemented pluggable. And then what COMPAS Seagull basically does is it makes a wrapper around the C++ code of Seagull. It exposes this as a Boolean module and then registers that implementation as the plugin for Boolean union mesh mesh in the category Booleans with then the implementation from the Seagull library. And so that means that then from then on, in COMPAS Geometry, you can, as soon, of course, as COMPAS Seagull is installed, you can use all of these Boolean operations from COMPAS Geometry through that pluggable object. So here you see a bunch of imports at the top, then a box and a sphere, which we're going to use to apply the Booleans to. Then this is the verbose version of the script, so you have to convert that box to vertices and faces because maybe here you see that these Boolean operations are written in a generic way, so they expect the input to be a list of vertices and faces for each of the meshes that it needs to apply the Boolean to. So here we first convert those shapes, so the box and the sphere, to a collection of vertices and faces, and both triangulated. Then we apply, for example, the Boolean union mesh mesh, the Boolean union to this AB mesh representation, and get back again a collection of vertices and faces, which we then convert to a polyhedron, and this polyhedron can then be visualized very easily with the viewer. And then the same for Boolean difference and Boolean intersection. Of course, that's all not very convenient and a little bit verbose, and so as I said, this is the verbose version of the script. That's a little bit what happens in the background, but COMPAS then provides or uses all of the magic methods and so on that Python provides to make this a lot less painful and a lot simpler. So instead of doing all of these things yourself, you just do box plus sphere, box for the union, box minus sphere for the difference, and box and sphere for the intersection. Yeah, and then once you add those three then to the viewer, you will see something like this. Sorry, I'm not entirely sure. Yeah, without this animated GIF, it's a bit difficult to show. 1 second. Oh. Sorry, that was not entirely what I meant to do. Entire screen. I think I'm just going to show you like this. Yeah, so now I think you can see. So yeah, we were here, and this was the thing that didn't want to load. So this is another thing that, for example, these plugins and then extensions or extensions to the plugins then add to the geometry library. So for example, if you want to work with NURBS curves, before in the COMPAS framework, this was not really possible. So if you wanted to, for example, discretize a NURBS curve and then move a box alongside that curve by computing a frame at every point of the discretization, you had, it's not very complicated, but you still had to do all of these things. So for example, you had to use a Bezier curve instead of a NURBS curve, and then discretize, so make that Bezier curve from a bunch of control points, then discretize the curve, and then basically compute the tangent and normal vector at every point of that discretization by doing an approximation over a window of 3, or a sliding window of 3 points along that discretization. Yeah, and by the way, here you see again, so the primitives being used in the background, right? You would have to then, for those points combined with those tangent and normal vectors, this would give you a point, a tangent, and a normal vector from which you can compute then the frame. And then once you have all of those frames, you would compute the transformation. So you would use the first frame as the base frame, and then compute the transformation from frame to frame to move that box always to a different position onto that curve based on where it actually then is on that curve. And then to make this animation, add this to the viewer, much in the same way as before. So you make the viewer. You add a curve, you add the box frame as a starting point, and then add also the box, but keep track of the box object. And then the viewer has this very convenient decorator that allows you to mark a update function or whatever function you want to use as a callable, or as a dynamic drawing function. So here, for example, you see that the viewer will on an interval of every 100th of a second for the number of frames that you've computed along the curve, will move the box object to that new position by updating its transformation matrix, and also add that frame that it's currently moving to the viewer, so that you actually see what is actually going on. And this is something that, of course, is much simpler once you have COMPAS OCC installed, and then through the same plugin mechanism, NURBS curves are available directly through COMPAS Geometry. And then all of this is reduced to 3 simple lines, right? Because you don't have to compute this discretization in the frame in an approximation by hand anymore. You can just make the NURBS curve, and then over the curve space, you take the frame at the parameter at that point in the space, and then do the same thing to compute the transformations from frame to frame with respect to the base frame. Yeah, and then the rest, sorry, the rest is exactly the same, but so that basically means that you can, yeah, the entire script for actually generating this this animation is literally that. Okay, so that's a very rough overview of COMPAS Geometry. So basically, the stuff that you get from the base Python implementations, and then all sorts of additional things that are made available once all of these core extensions are installed, but which then give you access to sophisticated libraries and C++ code from OCC, from from Seagull and so on through the same simple-to-use API as you get from the rest of the COMPAS framework, and without having to bother with importing all of these packages and so on. The second thing I wanted to talk about that relates to this COMPAS data, and I promise I will circle back all the way to COMPAS data, are the data structures. So there are three data structures available in COMPAS, or three base data structures, because there are many variations and combinations available as well. So there is the network, which is an implementation, or which uses as a data structure a graph. So a simple edge graph, which is extremely versatile, but also a little bit limited in the sense what it can represent as geometry. So it's more something to encode connectivity between elements, which, by the way, can also be other data structures, other geometry objects, and so on. Then there is the mesh data structure, which most of you probably know very well. It's an implementation of a half edge. And then there is the vol mesh, which is a bit of a niche thing that we actually almost exclusively use for 3D graphic statics. So the vol mesh is, let's say, a 3D translation of a half-edge data structure, which we call a half face. And so it works in the same way as a half-edge data structure, but then through the y directions of the faces between the cells instead of the opposite directions of the half edges between a face, between two faces. So I'm not gonna go through. I'm gonna be bold and try to do this presenting again. I'm not gonna go through network and vol mesh network because it's very simple, and I think that's yeah, something that everybody knows very well. And then vol mesh because it is so specific. I'm going to focus entirely on the mesh, and I'm actually also not necessarily going to focus too much on all of the algorithms that are available for meshes. Everything that you would expect from a mesh toolbox is available. You can work with normals, weighted face normals. You can find strips or loops on a mesh and strips. You can apply all sorts of funky Conway operators to a mesh to convert it to different topologies. There are triangulation algorithms available, remeshing algorithms. You can compute very, very simple duals, or it's very simple to compute duals. You can apply all sorts of modifications to the mesh, like delete vertices and faces, and et cetera, while keeping the mesh data structure perfectly intact. You can apply all sorts of funky subdivision schemes, like here frame subdivision, and then thicken the mesh, et cetera. So the number of algorithms available is really quite extensive. But the thing that I wanted to actually talk about with the mesh data structures, which relates to this data framework that I said was so fundamental to this communication between different softwares and between different processes. And so what I wanted to highlight is that the data structures, and this applies to the network, the mesh, and the vol mesh exactly the same. Also, in terms of the algorithms and the API, they're extremely similar. But so the data structures do not only allow you to store geometrical data and then the topology of the objects that you're constructing, but they also allow you to store any additional arbitrary data that you want to include in or store on vertices or edges or faces or on the global mesh itself. And so here, for example, if we create a simple mesh from a few vertices, so this is just going to make a simple square by adding a quad face to the mesh. If we then plot or print the vertex attributes of vertex A, you will see that it automatically stores X, Y, and Z, of course. So this is the geometry. And then the edge attributes of edge AB, for example, are going to be empty, and the face attributes of the face of that single face that we created are also empty. And that is because the mesh by default, so it stores a bunch of default attributes. So it by default stores the geometry of a vertex, but it doesn't make any assumptions about what you want to store as additional data on edges or faces, nor what general data you would want to store as attributes of the mesh. So it will only store actually the name of the mesh. But you can, in a very flexible way, I mean, you can obviously customize the mesh class and then add as many attributes and methods and functionality as you want. But you can also just, like you see here, simply take the base implementation and then update the default vertex attributes with, for example, here an isFixed attribute. We have the tendency to prefix everything that is supposed to return a Boolean with either is or has. And we give it a default value of false. And then there is, we update the default edge attributes with, for example, a weight parameter, which by default is 0. And we update the default face parameters, for example, with custom normal that we would want to align the faces to in some kind of a parallelization algorithm or something like that. And so then when you would plot these default attributes again, you see that now indeed the vertex has added to the X, Y, and Z that it already stored. It's added on this is fixed. And then the edge has this weight and the face has this normal, which by default is null. And then this, once you start adding vertices, you will see that, for example, if you then add vertex A, you can specify that this vertex then, for example, needs to be fixed, whereas B, C, and D do not. And then when we plot the vertex attributes of A, we will now see that it's this is fixed is no longer false, but is set to true, and that AB or the edge AB and the face have received these default attributes. And then there are a lot of mechanisms to access these attributes and update them either one by one or multiple attributes at a time. And this is a little bit done by convention. So if you provide singular, so vertex attribute, that means that you want to access one attribute of one vertex, whereas if you say singular plural, so vertex attributes, that means you want to access multiple attributes of a single vertex. And then the same with the plural singular and plural plural. So vertices attribute means one attribute of multiple vertices, either all vertices or a specific selection that you ask these attributes for. And then plural plural is multiple attributes of multiple vertices. You can go completely bonkers with this. So it's not limited to one or two attributes. As you can see here, for example, in the high-low data structure that we use to exchange data between all of these processes and all of these tools. This is, for example, the data that was a part of the data because it didn't really fit on the screen. That was stored on on this particular vertex that is marked in red there. So some of these attributes related to the form finding process, others related to the fabrication process, some related to the structural analysis, others related to the control algorithms that we developed for this cable net, etc., etc. And so various people could tag on to this set of attributes, update them in a very transparent and consistent way, and move then these attributes from one person to another, from one computer to another, from one software to another, and from one process to another. How does that then work? And this is where I cycle back all the way to this COMPAS data part. So COMPAS data provides a base data class that is the foundation for all of the other data objects in the framework. And it provides a few attributes, for example, data type, a GUID, the name, and then a few of these typical Python magic methods, and then a few class methods to allow objects to be created from data, from a JSON representation of that data, or from a JSON string representation of that data, and obviously conversely also to convert to data to JSON string, copy an object, validate the data, validate JSON, and so on. So that's that base infrastructure that this data object then provides, and it provides this then to all of the geometry objects, all of the data structure objects, and all of the robots. And so here you see, for example, what this means for a point. So if you create a point at 0, 0, 0, the point will have a name. If you don't change it to something else, it will be point. It has a GUID, a data type, the fundamental data that it needs to reconstruct itself, and then it can convert itself to a string or to a JSON file. And the most important part in this process, of course, are obviously this data type and then the data representation, and then these conversions to JSON and to JSON strings and to JSON files. And this is true for all of the objects, right? So also for example, for a frame, but also for a mesh, for entire robots or robot models. So any object in the COMPAS framework actually implements this interface. And this has a few extremely cool side effects, because, for example, if you now have a script A versus script B, so script A can be on my computer, script B is on your computer, or it's in different softwares or on different operating systems or whatnot. And if I, in script A, make this point and I just dump this to a JSON file, I can then in script B load that JSON file again. And not only do I have access to the data, but I have access to the original object. So I will also have all of the methods and attributes that a typical point object in the COMPAS ecosystem would have, like this X, Y, and Z coordinates. And here, for example, for something maybe slightly more elaborate, a vector. So you have two vectors, u and v. One is parallel to the x-axis, the other parallel to the y-axis. You dump these u and v to a JSON file, and then in another script, another computer, another universe, you load this again from that JSON file, and then as you can see, you don't even need to make a vector out of it. This COMPAS JSON load will take care of all of that for you, and you can start using these objects again as real COMPAS geometry objects. So, for example, apply or compute the cross product between the two vectors, and then check with the dot product whether these two vectors or this new vector is then perpendicular to the old vectors, and so on. This is not only true for all of these simple objects, but this is also true, for example, for meshes. So here, for example, we create a point, a frame, a mesh. We add this to a list or a data list. This can also be a dictionary or a tuple or whatnot. We dump this to data. Usually when it's not a single object, I tend to call this a session. And then this session you can then load again on a different computer. Or for yourself, if you want to continue working on a later date, or if you want to move this data from one process to the next process. And again, as you can see here, you don't need to reconstruct this mesh, or reconstruct the point, or reconstruct the frame. You just get the point, frame, the mesh from this data, and you can continue working. It's not just individual objects, but you can actually also have these objects nested as far as you want. So, for example, here, this tube mesh that I've been using as an example throughout my slides. So we make from an OBJ file, we make this tube mesh. We then update the default vertex attributes and set, for example, a target attribute to none. As, for example, if you want to add a constraint to your form finding process, or you need to fix a particular vertex, or you want somebody else to fix a vertex to a particular target, you can set that as a default attribute. You can store, for example, an entire network as a default attribute of a mesh, or you can store it as a vertex attribute, doesn't matter. Then we, for example, for a particular vertex, in this case number 126, which was the one where you saw earlier the hole being deleted out of the mesh, we compute the point location, we compute the normal vector, we move the target in a small distance in the direction of the normal, right? So the point plus the normal times 0.5, so half of the normal. And then reassign this to the vertex, the target vertex attribute of this vertex 126, and then dump this to a JSON file. So we have basically now a mesh with all sorts of nested attributes, which are in turn themselves objects, and then even a network attached to it. I'm just going to go through this slide now, point per point, but so here we go. And then in script B, we basically can then just load this. So here we only dumped the mesh, right? So we didn't dump any of the other objects explicitly. And then we load the mesh back from the session file. We can keep working with the network as if as if it was created here. We can loop over the vertices. We can check if so we get the target attribute of each of the vertices. If the target is there, we move the vertex to the location of the target. And then we add all of this to the viewer. And then, for example, in this case, you would then get something like this, right? So this vertex used to be here, and it moved in the direction of the normal because it was snapped to the target through all of this data attributes and passing these data attributes from one process to another. This is basically the foundation of how all of these processes talk to each other and how we move data around and how you can really keep working with that data as if the data was live to begin with on your computer. You don't have to recreate. You don't need to know what type of data you have to actually recreate. You can just keep working with it. And as I said, there's really no constraint to how much data or how deep the nesting goes. You can really do this as flexibly as you like. Then I'll finish up really quickly. The only other thing that I wanted to point out that makes all of this moving around of things between all of these processes extremely flexible and extremely easy to do is the concept of artists. So we visualize everything with what we call an artist, and these artists, the base interface of those artists is defined in core COMPAS. That means, and then again through the plugin mechanism, I didn't highlight this here, so through implementation for these artists are provided by Rhino, Grasshopper, Blender, or whichever other cat tool you want to include in this. And that means that basically whether you're working in Rhino or in Blender, COMPAS code is actually exactly the same. So you get COMPAS, you get an artist from, or a generic artist from, you clear the scene, you load your mesh from your session file, you can keep working with your network, visualize the network. I didn't do that here, but that would also be a possibility. And then do the same thing as I did with the viewer earlier. So loop over the vertices, move a vertex to a target if necessary, and then visualize the target points. And then at the end of the day, also the final mesh. And then so that the two scripts are really identical. And then whether you then Rhino or in Blender, this really makes absolutely no difference. So all of that makes this process of using computational framework that we provide, all the geometry functionality, all of the data structure solvers, all of the topology algorithms, everything that is included in the framework, plus all of the extensions that people that build on top of this framework basically become extremely easily available across different softwares and across different platforms. I have one more thing to share, but before I do, I just wanted to let you know that I will make, so all of the images and all of the, all of the images in my slides are actually generated with script. So I for those who are interested, I will make all of those scripts available, so the one-to-one in relationship to the slides in this COMPAS Connect repository on the COMPAS Dev organization, so that you can try some of these things for yourself and see that it is indeed really easy to do a lot of sophisticated stuff. And then before finishing up, what I wanted to maybe provide as an outlook is that we take this do not repeat yourself or others, this O stands for others. We take that very seriously, and so we work very much on a computational core that can be used outside of CAD software and on multiple platforms, and can tie all of these libraries together and so on and so on. But we obviously want to align ourselves with all of the other projects that are going on in the open source community, for example, Speckle. And actually, Gonzalo wrote this yesterday, which was the first exploration of how Speckle could be linked to COMPAS. And as it turns out, because we both rely on JSON for our low-level representation of data, it's extremely easy. So the only thing that is needed is this little Speckle data bridge. And once you have that thing, you can convert any COMPAS object very easily to like for example here, a mesh to a Speckle mesh or a smesh, and then send that thing over to a Speckle server. And I have to be honest, I'm not entirely sure what exactly is going on here, but the point is that we are exploring and want to explore more in the future also how to align ourselves with all of these other initiatives in the open source community to really build a chain of tools that can be used together extremely easily to tackle all of the problems of our industry and the world. Voilà, that's it. Thank you very much for listening. I'm not entirely sure what is supposed to happen now.
Yeah, sorry, Tom. I was lurking in the background.
I was hoping that you would show up, Alan.
Yeah, I was just about to introduce the next. I was a little bit in both places. Sorry about that. I'm not sure if anybody has questions that they want to post in the chat. If you stop sharing, Tom, you should see the chat. If not, I think Gonzalo has been lurking around, already answered some of the questions that have been popping up while you were talking. So if anybody has any questions, now is your time. If not, we're very happy for you to have joined, and see you in the next chats.
Okay, cool.
Oh yeah, Alexander has some. I'm gonna leave you to it, but I'll lurk around to see just in case you need help.
Okay, cool. Thanks. Yeah, we can hear if you want to speak. Yeah, that would be a lot easier. I can actually also turn my camera on, otherwise I'm talking to a black screen. So is it possible to directly interact with commercial FEM packages? Yes. So what we are trying to do there with FEA and especially also FEA2 is like actually with Core COMPAS, to level out all of the differences and all of the idiosyncrasies of all of the different softwares and all of the different modeling languages and all of the different input files and et cetera, by providing an abstracted out language, let's say, that is very much in line with COMPAS itself. So if you know the COMPAS API, you know the COMPAS FEA as well, especially the FEA2 API. There is at the moment the FEA1 API has a bit of a gap with the COMPAS API, but that will be resolved soon. And so you can then all of the modeling of problems and modeling of the analyses that you want to do, you do then in a very simple modeling language. For those of you who know CVXPy, for example, that provides like a modeling language for convex optimization problems. So you can think of it as something like that, where you, in very human readable terms, specify the problems that you actually want to tackle. And then you basically hand this off. So COMPAS FEA or COMPAS FEA2 then translates this into the format that particular FEA tools actually understand, and then hands this off to that FEA tool and gets the results back, converts this back into that FEA modeling format so that they can then be displayed in Rhino, Blender, the viewer, the browser, etc., etc. Have you received many external contributions to the project so far, and how have you been handling them? Well, this is actually something that has been increasing quite a bit. So people, so there are two things. There are the packages that COMPAS Dev creates, and so that's the core development team. And so this is something where we do all of the quality control and that we make sure that everything is nicely compatible and so on and so on. To manage the compatibility between Core COMPAS and the let's say third-party contributions, we provide a lot of templates for people to start from that create basically Python packages that work extremely well with the COMPAS framework and have everything already from GitHub workflows to releases on the Python package index, Conda releases, etc., already set up. With also a particular package structure, with everything for the documentation already in place. And then if people then still need help to how to then work with this template, at the moment there are not too many tutorials available for that, but then we basically just help them out to get a handle on this, but usually that goes extremely fast. And so lately, quite a few packages have been popping up, and I've actually yesterday received a message from someone at EPFL who has released the first UI tool entirely built upon COMPAS without actually us being involved for wood joinery. That, for example, also uses COMPAS FEA to then do analyses of all of these components. I see some opportunities to implement structural topology optimization into the COMPAS framework with something like PETSC. Is this something that's on the horizon? Well, there are some very basic topology optimization tools available, but they're really more playful experiments. Francesco Ranaudo has been actually working on things like this for his research. And since we expect all of our researchers to, at the end of their PhD, publish their work as a COMPAS package, I can imagine that something like this would be available soon, yes. I saw earlier, all the way in the beginning, I think, A question about IronPython. So yes, absolutely. You can use COMPAS directly in Rhino, so you can use it in the Rhino script, in the Rhino Python script editor. You can use it in a Grasshopper component. We have taken great care to write all of the COMPAS code such that it is backwards compatible with IronPython 2.7 where necessary, and uses all of the bells and whistles of the Python 3 where possible. So for example, Blender, where we can use Python 3, there everything is, for example, type annotated. The plotters and the viewer, where we automatically are not in Rhino, there also everything is type annotated. We use all of the latest possibilities of Python 3 and so on. But for example, COMPAS Rhino, and then all of the pure Python parts of COMPAS that we want to be available everywhere, they are written such that they are backwards compatible with IronPython, well, Python 2.7, but then also IronPython 2.7. Alan, am I correct to assume that people have left?
So I guess there's no more questions from the audience. I guess they will leave them all for tomorrow's session on COMPAS.
Yeah.
That one would be way more, so that's going to be cool. We'll see you all there.
Yeah. Ciao, guys.